there any other questions for the Q-learning? So we're going to move on to deep Q-learning. So we continue with the deep Q-learning, and then we take a break after the deep Q-learning. So is all right with everybody? Okay. So we're going to do the deep Q-learning. And if you remember correctly, so what we do, we kind of estimate the value of a state-action pair, right? This is what we're doing in a nutshell. And what it was here in the Q-learning algorithm, it was a table. It was just a lookup table. We just stored it in memory. And in deep Q-learning, we say, okay, instead of being at the table, it's going to be some type of neural network. And the neural network takes as an input, it takes the state. And it returns me the Q value for every action. And what's the cost function? What do I optimize the neural network for, right? So it's kind of the TD error, right? So we have now the neural network estimate of the state action minus kind of the beta estimate, which is the reward plus gamma of the maximum possible reward of the next state. And that's pretty much it, is it? And then you take this, you calculate the mean square error, and you backpropagate it through the network. And because in neural networks, everything is done through batches, so there are a lot of kind of little special adjustments you need to do. But in a nutshell, that's it. That's it. So I kind of have my neural network machine. I put in my states, and I get like my Q value for each state in action. And then I calculate the error of these Q values against the expected one. Get my TD error. And that's what the pseudocode looks like. And so there are any questions from stuff before we go through this together?
Is episode the same as action or state or something different? Right at the beginning, first line.
First line.
For each episode, one and n do. So it's like one game, like one round. So for one game, for each step, basically. T are the steps. It's the same, it's just going to be iteratively. But okay, I'm going to talk more about it soon. Just have any people like questions to what happened before, like with the neural network. Just use a neural network and we kind of calculate the mean square error. All right, so there are a few tricks and changes here. So basically, we just initialize like a random model, pretty much, with a random neural network. And we start playing the game. And we do like a random step. And we do like an epsilon greedy, which means with epsilon we do a random action, else we take the maximum greedy. So we put on our state in, we get the value function for each action, we take just the one with the highest predicted value. And at the very beginning, it's just going to be random, because in our network it's going to be random. And we execute the action, and then we get the reward in the next state. And what we do is we get this next state, and we store the transition. And we store the transition into a memory. So we have a state, action, reward, done, and next state, transition, and we just store them. We keep playing the game. And then when we say, okay, we have enough transition, like we do a mini batch on all our stored transitions. So if you have stored enough transition, at the beginning we just do random steps. And we have enough of them stored in, we gonna do our backpropagation. So at the beginning we just play until our memory is full enough, and then if we have enough, at every step we draw a mini batch out of it, and we're gonna train the network. And they store this in the memory. I don't store these probabilities. I just calculate them on the fly. So this is kind of like the the model parameters.
Sorry, and transition is the difference between two states?
The transition is like one step in the game. Like each, they call them transitions. So transition is like one step. It's like state, action, reward, next state, done. So it's 5 things. Think of it as an array, a list, a big array, and when the array is full, we say the array has a capacity of 10,000, we just start overwriting at the beginning again. And this is called the replay buffer. And they do this because if I would just linearly always train with the data from my next step, all the steps are like random, are highly correlated, right? So your next step and your previous step, the data point is very correlated. So they say it's better you just store your transitions in memory in like a replay buffer and you randomly draw from it. So you get a more diverse set of training data points.
Can you just explain the episode part again? Like for the other ones, I sort of understood that, okay, it could be terminal, say for instance, if an episode could be terminal or it could be something like that. But here in images, how would you define that? Like here it says image xt plus 1, so I wasn't able to understand that.
Episode is like one round of the game.
So how would we define rounds when you're looking at images in this case?
Images.
What does it say? RTN image xt plus 1.
And image xt plus 1. Like image xt plus 1 because it's the deep Q learning paper. They did it on images, but it's just the next state. It's just the next state xt plus 1.
Okay.
So the state can be anything.
Okay.
Can be literally anything. Can be 4 vectors describing your position in the space. Can be an image. So they use, I have the convolutional neural network. I have it here, and you can take a look at the code. I will not go through in detail because of time limitations. But all the examples I do, they're going to be like, it's just cardpool. Just for time limitations. So if you want to train, say, the real deep Q learning algorithm takes a long time just to run. So if I get time over the weekend, maybe I'm going to run it on Google Colab, and then I see if I get a good trained model, then I can show it next time. But essentially, you just store your next transition, next state. And episodes is just the same as with the Q learning, right? We had like, you play 10,000 rounds of the game. And then we say we do 50 steps, 50 transitions in that game. And for the 50 transitions, you're either done or you are just stopping and you start a new game anyway. And that's it. And now this YE is kind of our target, our error, or a true label we want to predict. You can think of it a bit like a regression, right? We're just trying to learn a regression. The neural network is regressing, and the input is the state, the output is this YE, and we try to be as accurately as possible in predicting the YE. And this is your error. It's like YE minus, I'm going to explain this soon later. This is basically the output of the model, and then you take the MSE square error and you back propagate it. And this is not the really true vanilla deep Q learning algorithm. This is already the one step advanced, where they have a target model and they have a training model, kind of. So you have this, your model. Oops. So you have this one model, you just use this to draw your next transaction, right? And then you say, okay, this is the model we're going to predict. And then every C steps, this is the model we optimize, we improve. And every C steps, you just copy the weights to this model, to this kind of, this model helps you to estimate the error, kind of. And they do this is, if you use the same model for these 2 steps, you generate like a moving target, right? So each time you run a step, you kind of improve your model, and then your error of what you're trying to optimize changes with each time. So now they say every 500 steps, you just update your weights, which allows you to generate 500 episodes or 500 data points where you have a fixed kind of target error. And what's this going to happen? How is this YE calculated? So if it's the final episode, if the episode terminates, it's just the reward, because there's no future discounted rewards. And if it's a non-terminate episode, it's the current reward plus discount factor times expected future rewards, the maximum possible future reward. And how is the maximum future reward calculated? I take this target model and I put in the state, right? I put in the state and I get the action value for every action given the state. And this is the future state, the next state. This is the next state. And I take the maximum value of this. So it's the same story again. And then this is my YE. And then I calculate the error between this. Because this is the action I took in that step, right? In that transition. So it's going to be one concrete value, and this is one concrete value. So in the end, I have two vectors. Take the difference of these vectors and take the mid-square error of it to get the total error. And then take this total error and I backpropagate it through the model. There are any questions? I think it's a lot to take in, and I'm gonna be straightforward with you. So the theory part here is a little bit the easier part than the actual decoding part. Because the theory part is just what we did before with a table. We just do a neural network. It sounds very easy, right? Yeah, just neural network, right? But there are like so many small things you need to do for the code that it's just all logistics just to deal with all that stuff. And on top of this, the way I coded it is going to be very object oriented. So if you don't have any experience in object oriented programming, just pay a little bit attention, because I'm going to go through a few concepts that can be very, very useful to you, including like abstract classes and interfaces and these kind of things. And the reason I do it is because after this, we're going to do Rainbow, which is just we do 8 improvements on top of this vanilla deep Q learning. And because I programmed everything object-oriented, you're going to see, okay, if going from deep Q learning to double deep Q learning is going to be 5 lines of codes. And that's the power of object-oriented. I just updated or changed the parts I need to change. But for this, to get this, there's going to be a little bit of upfront cost at the beginning. Let's continue. It's gonna continue with the code, and I'm gonna go through step by step. Everybody, hello. And breaks over. Let me restart the run. So if you continue this, I recommend you to restarting the runtime and to run this function. So it's gonna install all kinds of things which you will be required to. If you want to look at the video later on, you want to look at the agent, you're going to require that.
Was that the actual one we were using? No.
So some technical difficulties here. Okay. So who has yes?
Do we need this XDPY info for this, because it says that it cannot install? Yes, I guess.
I guess so, yes.
I already tried to install it, but it doesn't.
Which one? XDPY info?
Yeah, XDPY info, yeah.
This one? This gives error?
Okay.
I'm just check. It should work. Now matching distribution font for. I guess it works even without that. And this it worked yesterday, or it worked like a few weeks ago when I wrote it.
Yeah, it doesn't work.
Okay, let's just continue, okay? So who ever heard of named tuples? Named tuples. Named tuples, you just you can define like kind of like a class. It kind of treats like a class definition, and it allows you to store the values in those fields. So if I have like a transition, I can write something like my T is transition, like say A, B, C, like more like this, 1, 2, 3, 4, 5, and then I can say, okay, my T dot state, it would return 1. And if I say here, it would be like 1, 2, 3, 4, it would return this 1, 2, 3, 4. Because here I define the name of the tuple, and here I define the fields. So I have like 5 fields. And this
enums?
no, it's not enums. It's a way of creating like a named dictionary. So this dictionary just allows me to access the fields. Sorry. And here I'm going to go through the replay memory. And this is just a helper function. You can just take a short look at it. It doesn't really help you much. It stores the transition. Like I say, I have a maximum size. I have a memory, so it's an array. And I have like a position, which is like the current point where I insert the next transition. And with push, you add a transition into it. And I add it at the position, and then I move the pointer by 1. And if the pointer is the very end of the array, it just moves back to the beginning. And that's it. And if I say sample, you just randomly sample some points from it. And so here I'm going to define like an abstract deep Q neural network. So this is like all my deep Q networks, and this is just the neural network part of the deep Q agent. So the deep Q learning consists of 2 parts. One is the neural network part, and one is the agent, or like the Q learner kind of things, right? One is the Q learning part, which kind of optimizes and know how I calculate the error and everything, and how I play the game, blah blah blah. And this is just the neural network part, like kind of how do I estimate this Q values, state action values. And it extends nn.modules. This is for like, if you're familiar with PyTorch, if you're a neural network, you just extend this interface. It just lets PyTorch know, okay, it's neural network. And what I do is like I have an init function, and it says, okay, it's a neural network. I have an input dimension, which tells me what's the size of the input. So if it's an array of 4, it's going to be like, array of 4, like a tuple for 1. If it's an image, it's going to return me like the dimension of the image, like 200 times 300 pixels, so times 3. So we have 3 color values, and so on. And the output would be normally the number of actions you select, normally, in 99% of the cases. And then we said, okay, FC, this is like kind of the feature generation, the feature generator. And feature generator here, in a very, very general sense, is going to be like some kind of neural network pre-processing. It takes the raw data, and the output is set kind of like a hidden state, like the features. And then it has a O part, like a O layer part. This kind of take this hidden state and generates the output, the final output prediction. And the init part initializes it. That's like how you initialize. So in this part, you're going to write the architecture of the neural network. And the forward basically tells you how to do the forward pass for the outlier, output layer, and the forward pass for the feature generation layer. And if it's a very simple, very straightforward vanilla deep Q learning, it's just going to push it through the layers. So just make a forward. It's just very typical normal forward pass. And then there's going to be like the forward, which is like the whole forward pass of the deep Q network. And what do we do? The input is going to be a state. So if it's a Atari game, it's going to be the image. If it's like whatever game, it's going to be like the vector of the figure or whatever you want. It's just the state of the environment. And this is going to be like a fixed one. So we're going to say, okay, you can write in the forward layer and then the future layer, whatever the layer are, and however you treat it internally, but the interfaces between these is going to kind of fixed. And what we're going to do is like you do a forward pass, and then you get the features, then you flatten the feature, and you pass it through the output layer, and the output layer gives you some kind of out prediction. So if a Q learning is going to be one single value, and then you return the out value. And this is just the framework, the interface, right? It has no meat, it has no real implementation. And it just lets people know, okay, how do you interact with this kind of networks that inherit from it. Like that implements this interface, they have to implement these functions, and these functions like how the world communicates with this network. And this is now the fully connected. So this is just a very vanilla one. It just consists of dense layers. How would you do it? And as you see, everything is fixed. Just the things I can play with is what's the architecture. In the init ones, you define the architecture, and in the forward ones, you just define how it is run. So we say, okay, we do two dense layers, and then another dense layer for the output. And for the forward pass, we just pass it through the dense layer. And then we pass the output, the hidden state, through the output layer. So are there any questions for the so who's familiar, whoever did some PyTorch? Yeah, so it's kind of break up into puzzle pieces, which you can kind of interconnect and play with each other. But if it were like just one layer, it would be like, oh, whatever, n dot sequential, and then it's gonna be like and then linear, right, and then input and hidden, and then you say whatever, reload or dropout or whatever you have, and then you do whatever, and then you say okay. Oops. So you get the idea, right? And then some hidden, and then you have some output, right? And then it would be just one and then sequential. But by breaking it up into like a feature generation part and into an output part, you will see later a lot of algorithms that improves on the deep Q learning, they play around with those two parts. So this allows us to exchange and modify them without having to recode anything. We just change this one part. We just swap it out with what we want to do.